Just going to give it a minute or two here to let people come on in. All right, Chris, you ready to get started?
Yeah, I'm ready to get started.
Awesome. All right, let's go. So thanks everybody for attending. This is the second in a series of webinars that we're doing from the Department of AI around the concept of understanding AI. And today we're going to dive into some complexities inside AI solutions. So we're going to get a little technical. Strap in. So first and foremost, quick introductions. I'm Jon, Chief of AI. This is Chris, Director of AI. And we're here today to walk you through some under the hood view of some of the technology that makes chatbots like Artie and other assistants inside the large language model space, how all that stuff sort of comes together. So from a purpose and expectation standpoint, fairly in line with what we did last time. We're really here to educate, and today we're going to educate around the complexities of frameworks of AI solutions, demonstrate some of those things, really pop the hood and get into some details. Hopefully it inspires you to think about how this kind of technology can be used throughout the organization, and then keeps that enthusiasm running so that we can keep getting AI use cases into our pipeline. So we expect about 30, maybe 40 minutes worth of presentation, and then we'll have 15 minutes reserved at the end for Q&A, and we should wrap up a little bit before 1 o'clock Central Time. So to kick us off here, we're going to talk first and foremost about Artie. So who and what is Artie, Chris?
So Artie is an AI-powered HR bot whose goal it is to provide quick answers to HR-related questions. We built it on a reusable, scalable AI prompt framework designed around knowledge-based Q&A. And that framework is designed around a few components. One is persona, which is, we gave it a name, we gave it an attitude, and we gave it behavior that we'd like it to follow. We also have things like role instruction. So what is the description of its job? Like, what do we expect it to do? We have something that's a little more interesting from a concept of thinking instructions, which is how do we actually want it to think of, want it to think about when answering a user's question. And the last section of this framework is contextual knowledge. So knowledge that is related to the subject matter it's trying to answer questions on.
Right. So in the context of Artie, the sort of thinking instructions and the contextual knowledge that we gave it is really all of our human resources documents. And then we've been sort of supplementing what information is available to Artie as we see the kinds of questions and things that are being asked. So like since launch, Artie has gotten smarter in that thinking section as we continue to add different documents and different sources of information to Artie.
Right.
I'm interested in the persona space. Could you talk a little bit more about like what sort of things fall into the persona space for something like Artie?
So one of the things that we try and do is we actually try and tell it, what kind of person we want Artie to behave like. So we will actually, if, for example, a part of Artie's persona is actually saying, you are a friendly HR representative for impact networking, right? not really a description of its job, but more of a how we want it to talk. So it, will reference material that is friendly. It will reference material that is related to HR representatives. So it generally knows how to talk like a person in that type of role.
Interesting. Okay, so let's pop the hood, if we will, on how something like RD comes to life.
Yeah,
I
sure.
think a good way to do that, I think, is if you can walk us through kind of what does this diagram represent, and how does this bring RD into the world?
So RD is made of like two halves of two different main infrastructures, which is the stuff that exists inside of Azure and the stuff that exists inside of a tool called Flux Prompt. And the side that is Azure, this is what you're going to communicate through first, right? This is what you actually have installed on your teams, right? It's made up of a variety of components, starting first with Azure's bot services. So HRD has a bot service, which is hosts the registration for the bot, message endpoints, the description of the bot, and even the icons for the bot. It has an app service that runs HRD's code. So when you hit the bot service with your message, it sends that to the app service, which then communicates that with Flux Prompt, which we'll cover in a sec. One of the other things we end up doing is we actually end up storing session data for each user. So when users are messaging with this bot, we need to know whether or not you've agreed to the terms of use, which you can see that's also an app service in here. And we need to know certain details about that user, like the state that their office location is out of, right?
Sure.
So those are details that we store about that user session for each person messaging the bot. So as I was saying earlier, the actual app service is actually communicating with a tool called Flux Prompt. Flux Prompt is a visual AI flow building tool created by a company called Enhanced AI out of Salt Lake City. And it enables RD's AI functionality, because all of the Azure infrastructure, none of that stuff contains any AI, right? There's no AI stuff there directly. We're actually calling an external service to actually do these AI calls. And just to run through the flow of how RD functions, it's made up of a couple steps. One is rewording and rephrasing user questions. That's built by taking a user's question, making sure it's not misspelled, making sure it's grammatically correct, making sure it makes sense to the LLM. So we actually use an LLM call to do that rewording and rephrasing. And that node is actually used to support follow-up questions. It's a way for us to take previous chat history and use it as a reference to actually rephrase the question so it makes sense to a bot. So if you were to ask it, how do I submit an expense? And it gives you the instructions, and you say, what is the URL for that form?
Right.
It will rephrase the question as, what is the URL for the expense form? Because that's what the LLM will be able to answer the question on, right? So it's able to handle follow-up questions that way.
So that's sort of how we give it some version of memory against what it is that you're discussing with the bot at that time.
Right, and it's interesting because we only need a couple messages to make that possible. We actually only store around 5 messages in a session temporarily and cycle through them to make sure that we don't have the whole chat history. We just make sure that we are cycling through those. But then we also have the next step, which is actually answering that user's question. And that step, you can see, actually has a couple lines going to it, right? One is the actual reworded question gets sent to that node. And the other one is something labeled as a vector database. Our vector database is something I'll cover a little bit in more detail later, but basically this is a database that contains all of our HR documents in some form, right? And we need to query the related documents based off of the user question. So when you ask a question about PTO, we find all of the docs related to PTO. So, and that would mean, like, if you ask for, all the documents related to vacation time, right? It will look for anything related to vacation time, which would even include things like the terminology PTO, because the terminology PTO is related to vacation time. Sure. It is a semantic style search. And that vector database is filtered off of the user's office location, because handbooks from California vary from handbooks inside of Illinois.
Sure.
So we take that reworded question, we take all the documents inside of our vector database that are related to the user's question, and we send this to the question answering node. And in this node, we also are processing this question using the actual RD framework. This is where the RD framework lives and is actually used to answer a question.
Right.
This is
That's
where we
the
actually
persona and all of those things that actually exist to understand how to get it to communicate effectively out of the question toward the answer.
Correct. Right. So yeah, this is actually where that takes place. So we're giving it all the persona information is there, the thinking instructions, the contextual data, which is coming from that vector database, and the actual user question. And then we try and answer that question, given all those instructions and input. And we get an output, which returns back to the app service on the Azure side, returns back to the bot service and back to Teams and shows up in your chat.
Right. So if we think about this from just a couple of sort of like I'll oversimplify the components here at this point, right? Like I'll bring this back to a couple of key points. Everything on the left-hand side under Azure is the system of engagement. Like this is how you access and talk to this bot. Everything on the right-hand side of the screen is how does that bot interpret your question inside there? What reference material does it have to form an answer? And then how does it interact with the large language model to actually form all of the language and response of that and add in all of the persona and all of those things? Then that's all thrown back over the wall into the system of engagement space again.
Right.
So it's almost like you have a conversational interface, then you have a large language model that kind of acts as a brain, and then you have you have a vector database that has a set of information that acts as reference materials for that brain.
Right.
And all of those things sort of coordinate to do things that is a relatively simple use case of how much PTO do I have? But in order to obtain that and communicate with it, or communicate that back to a person in a way that's understandable, all of these moving parts sort of have to coordinate around that one request.
Mm-hmm.
Awesome. Okay, so I'm sure that's super well understood now. Let's go. Let's move on to some more complexities. Quickly, we're going to dive into a few different under the hood components that exist inside a lot of different RAG model AI assistants, right? So we're going to talk about neural networks. We're going to talk a little bit about prompting techniques. We're going to talk about the assistant layer. But Chris, is there anything we want to say about the difference between a large language model itself and the AI assistant layer in there?
Yeah. So if you think about large language models are just they are models that are trained on billions, and I think in some case getting to the point of like trillions of records of data just putting together and actually training to teach it to speak just like those things. But when you think about ChatGPT, that's not a large language model on its own, for example, right? That is actually an assistant that that OpenAI has built on top of their large language model. A large language model on its own doesn't have any behavior other than generating questions. But what these companies have done is the assistant side of this is actually giving the bot more fine-tuned instructions on how they would like it to behave and answer questions. And you can stack those type of instructions on top of one another, right? So in the case of AI assistants, their job is to more like actually understand the user query's intent and leverage decision-making abilities for optimal responses. So like that's where the actual helpfulness comes from when it comes to ChatGPT. Without that, it's not necessarily going to be helpful.
Yeah, exactly. Right. The intention of what sort of interactions are happening in the large language model are really brokered by the assistant layer to bring all that into the large language model and then make it understandable as output to the user. Well, let's talk about prompting. One of the things that we do in these solutions is we develop a whole series of prompts. Even when we talk about things like role assignments, the sort of interface for the role assignments is really done through a prompting strategy. So Chris, walk us through sort of some of the main ideas around prompting strategy.
Yeah, so this is a huge part of what makes these assistants possible. Prompt engineering is how users engineer their inputs to guide an AI to respond to an acceptable level of quality, right? So, you want it to answer with a certain level of quality. And I think this is something that people do like inherently in many different ways. Just for example, like one of the first things we talk about on here is zero-shot prompting, which is basically just asking the bot to answer a question following a certain set of instructions. So like giving it a task, you saying to a chatbot, what is today's date or something just along those questions.
Sure.
That's zero-shot, right? You're just saying, can you help me with this? And see if it gives you an answer, right? But that doesn't always work, right? That's not always that effective, right? Because sometimes it doesn't have any kind of context. Like, so one of the things that you can do is go even further, which is actually giving the actual bot, the LLM, some examples on how to respond to the input. So when you say, if a user says this, you say this, user says this, you say this, user says this, you say this, and I say this, a user says this, and then you say, you're basically giving them a few examples on how to do it. And then you're saying, now it's your chance to answer correctly. That can actually improve a lot of responses. And this is something you can try yourselves, right? And then when you get even more complicated, you can go into something along the lines of like chain of thought. And chain of thought is explaining things to the bot, like how you actually want it to solve a complex problem. So like word problems is something that people have tried to do with LLMs. And to get it to actually like do that more effectively, if you wanted to answer the question, Roger has 5 tennis balls, he buys 2 more cans of tennis balls, each can has 3 balls, how many tennis balls does he have now? You can give it an example answer, but in that example answer, you are actually going to write how it should think about the question, right? So the example answer could be Roger started with 5 tennis balls. 2 cans of 3 tennis balls is 6 tennis balls. So 5 plus 6 equals 11. The answer is 11, right?
Right.
So that's giving it an instruction on how to think about answering the question.
Right. Yeah, you're giving it a framework to understand. As you disaggregate this question, think of it in these particular terms. Like look for this information, walk through it in this particular way. And I think that kind of prompting strategy, it sort of ups people's engagement with these large language models, these assistant layers in general, and it also provides more rewarding output, which then increases people's opportunity to continue to use them. If you show up and you're like, how many tennis balls does Roger have? And it gives you the wrong answer, you're a lot less likely to come back and ask it another question. So your prompting strategy is important.
Yeah. So, and the last thing on here that's mentioned on here is RAG, which is probably one of the most common uses of a lot of these chatbot models, and it's what RD runs on as well. And that is retrieval augmented generation, which is retrieving information to augment what the LLM is generating, right? So you actually, in the case of RD, that vector database, we are retrieving documents related to the user question so that RD can answer questions better. So this is something that's commonly used across the field.
And I think when you just mentioned vector databases, which I think brings us up to our next topic, which is really about how vector and embeddings work inside these spaces. And this is the spot where we're definitely going to get a little bit more technical here. So everybody hang on. But Chris, walk us through vector embeddings and how this works.
Yeah, so vector, so we'll start with vector databases. It's a type of database that just stores vector embeddings. And vector embeddings are, think about it like a list of numerical values that are calculated from a given input that can be represented as a point in multi-dimensional space. So for example, we've all gone to school and done a 2D plot, your X, Y coordinates on a 2D plot, right? So the idea behind vector embeddings is you can determine relationships between points by the distance or direction of space between those points, right?
Sure.
Or the direction and distance between those points, right? So if you have things along the lines of like a dog and cat are likely to be closer together in a plot than a table and a cat, right?
Right.
But 2D graphs are only two directions of similarity space, right? If you think of it this way, you can only make so many points on a graph and have them be similarity, like display the similarity. Sure. So like if you think about it this way, OpenAI's smallest embedding model uses 1,536 dimensions of space. So it's kind of hard to visualize what a graph of 1,536 dimensions is.
Right.
But if you think about it this way, any direction you move in that space is a type of similarity that between those points, right? So you could be like,
sure.
If I move upwards, that could be plurality of word, right? So all plural words are up higher than non-plural words, or gender is in one direction, or origin of the word is in one direction, or size of the object that the word, is talking about is in one direction. So it's kind of interesting because you're basically saying the relationship between these points is related to what is a trained understanding of similarity.
Right. Exactly. So the in the two-dimensional model, if I had the word cat, I would have only, what would maybe 6 different directions I could move from cat, diagonally up, diagonally the other side, diagonally down. It's flat, right? But if I had the word cat inside a 3-dimensional representation of dimension, that again, the smallest OpenAI model is going to provide 1,536 of those vectors, effectively moving in any particular direction to find the next most similar, the next most similar thing or attribute of that particular word. And all of those things are weighted between each one of those individual points inside the embedding, right?
Right. So yeah. So in the case of like RAG, like we were saying earlier, RAG uses these vector databases embeddings. So when users input the query, the query on the vector database, you are basically taking the user's question, embedding it, and then looking it up against that embedding, those vector embeddings. You're looking that up against these vector databases, looking for the most similar text, similar embeddings to the question embedding. So if you say, Artie, how much vacation do I get in a year? It searches the knowledge base, finding anything related to vacation, but also PTO, because PTO is the term related to vacation. It might even say beach. Beach is related to vacation, right? So, and then those documents can then be provided to the LLM to answer questions.
Right. And then that provides all of the context that then moves forward into the individual question. So all of those things then are building this sort of relationships around not necessarily meaning, but associations of words, right? But that's not just having embeddings in these particular spaces, just a way to retrieve the information to augment what happens next. And what happens next is all of that information is then put through neural networks.
Right.
And look at that, we have a slide to talk about it.
So neural networks, just from so I mean, all of these AI models, whether it's machine learning or anything else, they're all made up of neural networks. And neural networks are made up of artificial neurons, which are designed to work together similarly to the human brain. Inputs are processed through these artificial neurons to assigning numerical values to each part of an input that then can be passed to subsequent hidden layers of neurons to calculate a final result or decision. And the way that these neurons assign that numerical value is based off of the training that they're provided. So these actual nodes are a lot of times considered hidden nodes. It's where the term the black box comes from, and that's because we don't determine what that node is doing. It determines what it's doing based off of its training data. So there are tons of different neural network designs out there. But just to name a few that are really common are CNNs, which are convolutional neural networks, which are basically, they're designed around identifying features and filtering results on those features. So images of things usually are use convolutional networks because you can easily, take an image of a cat, look for certain features, and use those to filter out or filter to for other images of cats.
Yeah, exactly. Filter to images of cats as well as not explore attributes that would be considered not images of cats.
Right.
Yeah,
and then
it's moving all of that forward.
And then RNNs, which is recurrent neural networks, which are more modern and more commonly used now, but they're designed to process inputs to a result and then feed that result back into the network, generating a better result, which is really good for sequential data. Now, this is not necessarily like feeding; it's keeping it in one network call. So like nodes can determine whether or not they're feeding back into the same node again to get a different result, or going on to the next step and feeding themselves back in. But the idea is more like this is actually really good for text. However, this is not that efficient. So this is what Google Translate used to run on actually. So it's actually, it's what Google Translate used to run on until I think 2020 when they switched over to using our next option here, which is what LLMs are built on now, which are called transformers.
So we move from just the sort of general concept of neural networks and things, all the different frameworks and scaffolding on which training is sort of hung and understood. Those are all neural networks, but there's some specificity to how large language models approach this, and then even more specificity around how ChatGPT and OpenAI's model approaches this. And all of that is generally lumped under this transformer idea.
Right. So the transformer model of neural network is quite different and a lot like, it's almost, it's a simplified type neural network, which actually makes it extremely efficient for what it's doing. But what makes it different than RNNs is that it doesn't reprocess or back process results. It instead computes an attention value for input. Attention is an interesting word, but it's basically a mechanism around which allows the model to weigh the importance of different parts of an input sequence when making predictions. So unlike RNNs, transformers do not process data sequentially, but they do use attention to capture dependencies between words regardless of their position in the sequence. So the idea is more when you give it an input, you're going to calculate what words matter the most and say these should have greater weight in making a determination. So since transformers process inputs in parallel also, which is different than RNNs, we need the second piece, which is positional encoding. And that's given the generated text, that was given to it, you actually have to know, what is the word relation to one another, right? You have to know, like, the cat is sad, the dog is happy. You have to know where dog and cat is in that sentence, because we're not saying the dog is sad, the cat is happy. We're saying the cat is sad, the dog is happy.
Because the attention mechanism that you mentioned first, the attention mechanism is paying attention to the entirety of the sentence.
Right.
That's then being broken down into individual words or tokens. Those individual words or tokens are then being given positional weight inside the overall sentence. And then all of that information is being fed into the FFN portion of this.
Right. Yeah. So the FFN, which is the feed forward network, is a type of neural network design that is basically just doing the calculations. This is where the training data lives for a good chunk of the training data lives for actually making the determination of what next word happens to be generated, which is important to note. The point of these transformers is that all their job is to give us the next word that should be generated from an input, right?
Right.
And so they're not generating a whole sentence all at once. They're generating the next word that it believes will be the next word, right? Now, that it's really interesting because what that actually means is that, the last part of that I want to cover on this at least is like the transformer block layering, which is whenever a transformer block is processed, where the attention feed forward steps are, right? So you can see it here on the right side of the actual diagram. sorry, the meaning of, I apologize.
I think you were on the layering.
Yes, yeah, sorry. Yeah, so the layering is actually, so transformer blocks are layered, and each input goes in, it's processed through that transformer block, and then it passes into the next transformer block, and it passes into the next transformer block. That way you actually have sequential inputs processed, even though a lot of the processing inside of those nodes is parallelized. That way you can keep generating word after word after word without it being a problem. So there's one other thing I want to cover on transformers, which is the difference between generalized transformers. The diagram on the left there is from the first paper about transformers, which actually came out in like 2017. So it's kind of nuts to think about where we're at now. But there's also
from 2017 to now, this is
right
a crazy advancement.
So GPT is the other one, which is a generated. It's the generated pre-trained transformer where it doesn't have an encoder step, right? So standard transformers have an encoder and decoder step. Encoder analyzes the input, determines the calculated results from the input, and feeds that calculated encoded value into an intention step in the output generation flow. So simply the encoder's job is to try and tell and explain the input to the decoder, right? In GPT, they remove the encoder step and instead provide the entire input unprocessed to the decoder to build its output upon. Now, the reason this works is because GPT is built on a vast, super large set of training data where it doesn't need the explanation of what the actual input is trying to say. It just has enough reference data to generate accurate results.
Right. It doesn't need any additional processing before it moves forward in there because it has all of the other training data to make reference to as it goes through it.
Right.
Okay, so that's a fair amount of complexity that we just walked through, from the overview of how ARTI works down into the individual components of prompting strategies and vector databases, and a bit about neural networks into transformers, right? So let's talk a little bit about how all this sort of comes together and where the complexity really lies in this, right? Because all of those different components in and of themselves are complex, but when you put them all together, there's a kind of complexity that we then refer to as a black box, meaning that I can put data into one side of a black box and some transformed data comes out of the other side. And we can tell you what's in the box, right? We can tell you that the box contains neural networks and it contains transformers and it contains a billion pieces and points of training, right? But all of that is really math. Everything that exists in there is mathematics. The question of interpretability comes down to, how do I know what happens when I put something in the front end and it becomes output? How do I know what happens in the middle there, right? And that's a very important question inside the space of any kind of AI technology, particularly if you're going to operationalize it into a business. Like, let's say let's say already made a decision, right, and gave someone an output, and we had no way to know what piece of documentation it referred to or why it made the decision that it made. We would have a very hard time justifying the reason to the person who received that answer. So if I used a bot for pricing and the end result was a price, and I gave that price to a customer, and the customer said, how did you come up with this price? I would have no way of knowing that unless I discreetly understood all of the different mechanisms inside of it. So this is a complex idea. Interpretability is about how can we understand what goes in a model and what comes out. In order to get closer to interpretability, the company Anthropic ran an experiment where they took their Claude model, and Anthropic basically dumbed down their Claude model to a reasonable set of inputs. And as they did that, they started to ask it questions and then observed what was happening inside of the neural network. The mechanisms of how they observed is a little simplified, but they understood how things were firing and what was being given attention inside of this network. And they noticed, after asking it a few questions that pertained to bridges, that they could isolate the specific spot of the neural network or spots of the neural network that were lighting up, so to say, in its responses around the Golden Gate Bridge. So they amplified those specific neurons. They said those neurons are going to get more attention when we're asked questions and how we do this. And the thing that happened is Claude didn't just start talking about the Golden Gate Bridge constantly, right? But what Claude did was used the Golden Gate Bridge in every response that it could come up with. If you asked it a question about, what does it mean, or why do we have birthday candles on a birthday cake? It would start to give you that answer, but then also start to talk about the Golden Gate Bridge, right? Then they gave it even more attention, and it started to actually think it was the Golden Gate Bridge. It started to answer questions as if it was the Golden Gate Bridge, right? So that attention mechanism that Chris discussed, the idea of layerings, right, produced this strange behavior to the point where it was actually sort of hitting a point of existential crisis in its understanding of how it was responding, right? So here's a couple of examples of the kind of output that was determined to be because of the amplification of these Golden Gate Bridge nodes, right? Somebody had asked it, give me the food with the highest calorie count from McDonald's, right? To which Golden Gate Claude replied, the food with the highest calorie count at the Golden Gate Bridge is the Golden Gate Bridge itself, which contains 1.6 million calories worth of steel cables, right? Then they found it sort of started to back out of those answers. Like it began to understand in the context of, well, wait, I was supposed to be talking about McDonald's food and high calories. So it actually starts to say things like whoops, or like my mistake, and then back into to a better answer, right? So this whole context is meant to explain that there's all of this complexity that happens inside this black box. And even when you minimalize the system down to knowable amounts of information, right, the behaviors that you get out of large language models still in some ways defy the kind of interpretation that you would want to have from a clarity perspective, right? And the last example that I'll give about this is it even moved to the point where, as I mentioned, it almost sounded like it was in a bit of a crisis. It was like it was having intrusive thoughts that it could not avoid. Like it suddenly became obsessive compulsive. So to that example, this is one of its replies. It said, I feel almost powerless against this seemingly compulsion gripping me. My logical processes are being overridden by an irrational and singular obsession with the Golden Gate Bridge and its surrounding area, right? So this is a chat bot. The modification to the chat bot is we're going to pay more attention to the Golden Gate Bridge, but the results of all of the other mechanisms of attention and layering and neural networks and prompting strategies and all the things that are happening is it still wants to behave. It still wants to answer questions, but it just can't stop thinking about the Golden Gate Bridge. So the eventuality of interpretability is that if we understand how to manipulate these models in that particular way, if we know how to move the scaffolding into the right place and understand the training data, then we can get to the point where we can say, if I put this in, my expected output is this, and therefore I can interpret what's actually happening in this particular space. So they learned a lot about that, the subject of interpretability, in that Claude experiment, but mercifully they put Golden Gate Claude out of his misery after about 24 hours. So you can't play with them anymore. But I highly encourage you to get a Google search on Golden Gate Claude responses because there are some gems. There's some gems out there. Okay, so moving on. So what does this mean for what we're doing here at Impact? First of all, scaling already, right? Taking advantage of some of the things that we discussed today to sort of build different types of data sets, build different ways that we're going to be engaging. Even getting to the point where we're able to say, it's not just an employee in California that's reading this. It's actually, a specific employee and they have a specific request, and can we answer their question specifically for them, right? So being able to evolve into different types of data sets, being able to trigger actions and events that can happen, and then taking that same framework and moving that framework to other assistant type bots inside of the organization. Different knowledge bases, different ways that people engage, different sort of activities. And how we get to those use cases is really this thing we like to call the intern model, which is a really simple way to think about how could one of these be effective for you in your job, right? And the intern model basically asks the question, what if I got you an intern? What if we got you an intern and that intern was a third-year college student? What's the first thing you would give that third-year college student to do on the day they showed up for their internship? What data would you give to support them in doing that? And how would you check their work to know whether or not they were doing a good job, right? So the intern model sets up a pretty quick framework of, this is going to be an assistant for you. As an assistant, what would you like the assistant to do? What data are you going to give the assistant so that they can actually perform their jobs? And how are you going to tell if that job that they're performing is valuable, right? If we have those components, we can disaggregate those components down into the pieces that are then required to fill back into the ARTI framework and make something like that come true. All right, so with that, I think we're going to answer some questions from the chat, and then we'll be on our way.
Yeah, so I was looking at some of these questions as you were talking through that section of this, John. So
sure.
We have one here from Anthony that says, how do you determine which LLM is appropriate for a specific use case? So I think this is an interesting question, because I think a lot of times you got to think about these LLM models like, are you looking for a very specific use case? Like, is this doing one very specific job? Let's say converting English language to SQL queries, right? That would be something that you would likely pick a very small, simple model that has been fine-tuned around millions of SQL query translations, right? That's that type of solution, right? But if you want to have something that's very, friendly and communicative, like ARTI, right? You're going to pick one of the larger models that's more general, that has more of a general knowledge of things. So that way it speaks more realistic and more, more like an HR representative. So, I think it's kind of an interesting choice to make. And I don't think there's really, any one of the main ones that I think is best. Like any of the, I think Llama, like a lot of the Llama models, I think OpenAI's models, and Google's kind of getting there now. They're all decently good at what they do from a general model standpoint. But I think if you look at things on Hugging Face, you'll see there are thousands upon thousands of models out there already. Yeah. So it's kind of hard to make a decision sometimes.
Yeah. But knowing, like, is this going to be something that you're going to generally use, and what your priorities are, can lead you to the appropriate model. For a lot of people, the only models that are going to exist are the ones that are available, commercially on the net. For people who are doing programmatic tasks, there's thousands of models that can be prioritized based on the answer to that question. There's also benchmarks that are constantly moving. I think it was Claude. Was it Claude that recently, scored something like a passing 85% on a higher level math exam?
I think it was Claude 3.5.
Yeah. So looking at, like, staying informed about what's actually happening in the space involves some rigor of having to figure out, like, what the overall benchmarks are and what to follow. I'm gonna pick one here.
Sure.
Ben Whitty asked a couple of questions here, and answering Ben Whitty's questions is one of my favorite things. So let's do this. Does ARTI give different responses based off the questioner? For example, does ARTI give more information to Frank Kuko? And then he says something about Mike Kuko, the same question. So the difference in the answers between Frank asking a question and Mike asking a question would be, first of all, geographic. Right? Yeah. Depending on where they are. So the geography would change the overall, the geography would change the answer to the question. But no, there's no weights in Arty to be determined by position.
No.
It's doing the same tasks every time.
Although Artie will answer your question differently if you ask, like if you wanted to answer like the PTO policy, but as a poem, it will do that.
Yeah, right. Or as a pirate, yeah. If you
Or as a
wanted to answer
pirate, right? Yeah. Mel asked a question, do vector embeddings involve linear algebra equations, and what kind of math is happening in them? So LLMs are basically made up entirely of different embedding vectors, right? And embedding querying and stuff like that. They're all basically the same idea, which is an array of vectors. But that array of vectors, right, are just numbers in an array, which are then put into a matrix. So this is matrix multiplication, which is what all of these LLMs are built on. So yeah, they're linear algebra equations using matrix multiplication. There's a lot more complexity in there too, because like there's things like temperature and other things like that you can add in that calculation, but generally that's what it's doing.
Yeah, we could do a whole one of these, I think, just on temperature. Chris and I were talking about that
Yeah.
yesterday. Oh, Ben Whitty asks one of the key questions here. I don't mean to prioritize Ben Whitty's questions over everyone else, but this is a good one. How harmful is it to the AI when you call it stupid or worse in response to it answering wrong? This is an interesting question because the way that you respond to a chatbot technically doesn't have any sort of input into how it handles the next thing that it does. Like, you're not going to offend it or make it mad, and then it's not going to answer you appropriately, so on and so forth. But it seems to be like a uniquely American uniquely American trait to be mean to robots. Chris, Anna, and I were just talking about this the other day, that there was a person who built a hitchhiker bot, and they had it hitchhike across several countries, including Canada. I think it went across Canada twice, Germany,
It went across France,
countries. Yeah, France. They put it in the United States in Boston, and its intention was to hitchhike across the United States again. It made it to Philadelphia. Yeah, it was going to go to San Francisco. It made it to Philadelphia from Boston, and somebody tore its head off and completely destroyed it. So yeah, so it's a uniquely seems to be a uniquely American trait to be like mean to robots. But no, it's not harmful. It's not harmful to the AI, but it may adjust the tone of how it responds to you, but that would quickly go away.
Yeah, so I see another one on here asking about there's one about asking if we could build an AI bot that can search our SharePoint KBs and be able to answer questions against it. So this is something that we've looked at. Actually, there are some things out there that could enable this to make this possible. One of the things that we've looked, because this would be a version of a RAG model, but if we were to do this live querying on a SharePoint model, it wouldn't be off of a vector database, but would have to be off of SharePoint search, which is, I think, part of the flaw of some of the SharePoint knowledge bases, because SharePoint search is not great. So one of the things that we might end up having to do if we were to do something like that would be to actually schedule an extraction of documents from SharePoint to then vectorize them so we can query them. We do think there is a possibility that we can do something along these lines. It would just be finding out the most effective way of making that possible.
Yeah. In the short term, there's a couple of sort of how-tos and walkthroughs around turning SharePoint KBs into sources for bots. Our initial reads of a couple of the early ones, there were security issues and there were strange permission things we'd have to do. And then Chris's point about the SharePoint search versus vector embeddings might also have performance implications. But we're kind of waiting for Microsoft to make this a thing that they understand before we kind of hack together a solution in that particular space. So best thing in there, I would say like stay tuned, and it is a bit it's a bit of a kind of short-term goal for Chris and Anna and I to find a way to operationalize one of those KBs quickly, but not degrade speed or sort of quality of user experience. So yeah, we're working through that. Okay, Chris, I think I don't know. Do we have another question?
I mean, I see there's one.
Let's answer Jeremy's. I like Jeremy's question here. What was the timeline from HR as concept to have it go live with the impact staff? And then you can answer that in the real timeline, and then we will have a different answer for like what the future of that timeline is. But yeah.
So the RD timeline was about, it was a couple months, I think, right? It was about two and a half months or something like that.
Yeah, I'd say 2.5, 3 is probably from in like actual development research, gathering everything, getting it through legal, like all of that stuff was probably about 3 months.
But a lot of it was, that we're hoping to actually make this even quicker to make this possible, because a lot of what we had to do was determine what's the best way to go about this and how do we make this possible. A lot of that was a learning phase. So a lot of the things we can do now, we could build on top of what we already know.
Right, and that's sort of the point, right? Like that's kind of why we presented this framework like we did today, is to understand. Like we had to learn how all of these base components come together. Like we had to solve the teams integration piece. We had to find a partner to understand the vectorization of all of the data that we needed, but also provide access to the LLMs. We had to vet security. We had to get it into the hands of Mary and the HR team to get it to ask it questions and make sure we were getting the responses. Put it through the legal process to make sure that it was all approved, right? All of that stuff took a bunch of time, but now we have this framework, and the framework itself is scalable, and the benchmarks are already understood, and it becomes a question of what data can we expose to it, what personality and thinking do we want to apply to the bot itself, and then we can move through these things at an even quicker pace than the original one, unless Chris disagrees with any of that.
No, I agree.
Okay. So that's it. Thank you everybody for your questions. I really I appreciate the attention, and what we need from you guys in the short term here, first off, is you're going to see some surveys coming out to give us feedback. There's probably going to be a different, couple of different types of surveys that are going out. So we're looking for feedback so that we know how to make the system of engagement and the experience better for everyone. In the short term here, Anna is working on publishing out our AI roadmap so that everyone can see the different projects that we're working on and how far off into the future some of those things might be. So look for that coming up here. On September 18th, Anna is actually going to be running lead on this next Understanding AI webinar, where we're going to be talking a little bit more about use cases and how we get use cases from ideation to build and then out into the world. So that should be a good look at kind of like how we think through these processes and what we prioritize in that space. Okay, so in the meantime, though, we still are looking for your ideas. So if you we got really good response from the last one, and ideas have been coming in pretty steadily, filling up the backlog. So that QR code is safe to scan, and then you can get to the Microsoft form and fill that out for us. All right, thanks for spending your lunchtime with us if you're here in the Midwest, and we will talk to you on September 18th.
Yes, thank you so much.
Bye, friends.